Right, so here we go with the trigonometry unit. This would be lesson 1. Our objective for today is to be able to find trigonometric ratios in a right triangle with known side lengths. All right, so as you can see, we have 3 triangles. They are all right triangles. We can tell that by the little box in the corner at D and A and G. What we want to be able to do in those triangles is identify from the perspective of the angle we know, that 30 to 33 degrees. We're not going to use the 90. We'll use the acute angle all the time. From that 33 degrees, which sides are the opposite, the adjacent, and the hypotenuse from that specific perspective? Right. So the way I think about it is, if I draw the angle bisector, which is just right down the middle, the side that I run into is the opposite side. The hypotenuse will always be opposite the right angle, which leaves the third side, AB in this case, to be the adjacent side. Let's do that in the other 2 triangles. So again, from our 33 degree angle, the side opposite will be over here. That's going to be DF. The hypotenuse will be opposite the right angle, and the adjacent side is the one left over. Again, one more time. We have opposite. We have hypotenuse at HI, and we have the adjacent side. All right, so what we're going to have you do next is an activity. We're going to give you rulers, and we want you to measure the lengths of each of the 3 sides in all 3 of these triangles. So you're going to get 9 different measurements. We want you to measure to the nearest 1/10 of a centimeter. All right, to the nearest 1/10 of a centimeter. I would suggest that you create a little chart here. We didn't create one for you, but I found it easier to have all the numbers right in front of me instead of having to look back up at the triangles all the time. So if you write the opposite, adjacent, and hypotenuse measurements for A, B, C for those 3, and then 3 here and then 3 here, you can then find those 3 ratios for each triangle. We would like you to round those to the nearest 3 places when you do that. So change the fractions to decimals, and then answer the question that's right down here. All right, so I'm going to give you a couple of minutes, or you can go on if you want, but we're going to pause for a second so you can do those measurements. All right, so I put in the measurements I ended up with. Again, 2.4 for the opposite side in triangle ABC, 3.7, 4.3. So opposite over hypotenuse, we would have the opposite side 2.4 over the hypotenuse, which I had as 4.3. Again, there's going to be some measurement error. Again, we don't have tools or implements to do this phenomenally well, but we should be at least in the ballpark. If we do that division, it's 0.558. If we continue across, we end up with 3.6, or the adjacent side over the hypotenuse, 4.3, which gives us approximately 0.837. Again, the squiggly equal sign is the approximately equal to, means we're rounding off, and we don't have an exact value. For the tangent, or sorry, the opposite over adjacent, we're going to have opposite of 2.4 over the adjacent side, 3.7, and that goes to a decimal at approximately 6, or 0.649. Continuing on, I'm just going to kind of run through these without a whole lot of explanation. Hopefully it's clear to you. We have opposite aside, again, that's right here, over the hypotenuse, 7.5. That's the longest here. Changing that to a decimal, 0.547. We then have 6.3 over 7.5. We get about 0.840. And lastly in that column, 4.1, the opposite side over the adjacent side, which we've got at 6.3. Gives us about 0.651. Last triangle, 1.6 over 3. Sorry, 1.6 over 3 gives us 0.530. I'm going to get rid of that. And call it 2.5 divide by 3, which gives us approximately 0.833. And 1.6 over 2.5, again, somewhere in that 0.6 range, 0.640 in this case, And then what are we noticing? Well, the hope is that we notice that those three ratios, all the opposite to hypotenuse, are pretty darn close to the same. And with our measurement error, they would probably be the same thing if we had accurate tools. Same story here at 0.837, 0.840, 0.833. Those are pretty darn close to being the same thing. Again, if we had good measuring tools, maybe they'd even be exactly the same. Last column, 0.649, 0.651, 0.640. Again, we're within hundredths or thousandths of each other, which is kind of a nice deal. We're thinking that those are probably the same ratio no matter how long the sides are. As long as those angle measures are the same in a triangle, the ratios of the sides are going to be the same. So the question is, how can we use that? Well, again, if we've got a 33-degree angle here, again, different triangle than all the others we've had, that the hypotenuse is 7.64. Again, that is the hypotenuse. I'm going to call this side opposite the y, and this side adjacent the x. The question is, how can we find the lengths of sides if we know what we know from above with that 33-degree triangle, or angle triangle, and the 7.64? Well, if we take a look at the opposite over the hypotenuse, we would get y over, 7.64. But that ratio for opposite over hypotenuse is right here, and I'm just going to take the middle one of mine. You can take any one of yours you'd like. And then to solve that, we'd simply multiply both sides by that 7.64. We've done that since about, what, 6th, 7th grade, where we get rid of dividing by multiplying both sides by the same thing. Again, those are going to cancel out, leave us just the plain old y. And if we multiply those two values together, we're going to end up with something like 4.18. If we continue on to finding the x value, again, the x is the adjacent side. Again, adjacent over hypotenuse. That would give us the x over 7.64. Sorry, having a tough time writing on a small screen. That should equal, again, that second column, that's the adjacent over hypotenuse. Again, I'll take the middle value, that'd be the 0.837. And to get rid of dividing by 7.64, we would multiply both sides by 7.64. 7.64's top and bottom equal 1. So x would equal 6.39. Real quick check. Again, the hypotenuse should be the longest side, and 6.39 and 4.18 are smaller than that, so I think those look okay. And the 33-degree angle would be the opposite side. That'd be the y value, and that is smaller than the 6.939. And that should be the case because the angle up here is 57 degrees. Again, 33 degrees and the 57 degrees have to equal 90, so that the 90 there plus the other 90 for the right angle give you the 180 for the whole triangle. So I think our answers look pretty good. Let's continue on to see what we're going to talk about next. All right, so turns out that there's nothing special about the triangle we just worked with respect to the ratios of the sides. That 33-degree angle can work, but so can any other angle as long as it's acute in that right triangle. So people found this so useful that they actually we created a branch of mathematics called trigonometry. It's often used by land surveyors to make maps of the world. I would also tell you that construction people use it quite significantly, as do machinists. So lots of jobs out there that will use this heavily. All right. So when you can't measure something or get to something physically, you can actually draw a model of it, and you can find the lengths of sides and measures of angles by using trigonometry. Again, that's with right triangles. For today, our job is to learn the big three. The big three are sine, cosine, and tangent. I'm going to actually write the whole word out for you. That's sine, cosine, and tangent. We do abbreviate those as SIN, COS, and TAN, but they represent, or they're said, sine, cosine, and tangent. Their definitions: sine of an angle theta is the opposite side divided by the hypotenuse. Cosine theta is adjacent leg divided by the hypotenuse, and the tangent is the opposite side divided by the adjacent leg. Now, there's a memory gimmick that people use. So Well, it's not being nice to me. So, ka toa, again, the so, it represents the sine, right, is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse, and the tangent is the opposite over adjacent. So again, memory gimmick to help you remember that. Let's get rid of this at the bottom, and let's continue on. All right, so from our theta here, which is a Greek letter that we use to represent an angle, we would notice that our opposite side is the length 4, our adjacent side is the length 3, and the hypotenuse, again the longest side, is the 5. All right, so they want us to write the sine of theta as a decimal. So we have sine of theta is the opposite side over the hypotenuse. That's going to be what? The 4 over the 5, which is 0.8. Again, you'd want to use a calculator to do that if you're not comfortable with that division in your head, or just don't know the point, or 4/5 is 0.8. If you want to go to cosine, cosine is the adjacent side over the hypotenuse. In this case, that would be the 3 over 5, which is exactly 0.6. And lastly, tangent. Tangent is the opposite side over the hypotenuse. Again, that's the opposite over the adjacent. My mistake. And this will be an exact value, I'm pretty sure. We get the opposite side 4 over 3, which is actually 1.3 repeating. All right, so SOHCAHTOA, sine is the opposite over hypotenuse, cosine is the adjacent over hypotenuse, and tangent is the opposite over the adjacent. We're almost there, folks. Hang in there. All right, so lastly, we want to use the triangle at the right to answer the next bunch of questions. What we want to notice is in the first 3, we're talking about this triangle from theta's perspective. All right, so let's do that. From theta, 5 is the opposite side, hypotenuse is the longest side, that's 13, and that leaves 12 to be the adjacent side. So from theta, sine is the opposite over hypotenuse, that's going to be 5 over 12. Sorry, getting set up here, which is approximately 0.385. If we go to cosine, cosine from theta is the adjacent 12 over the hypotenuse 13, so that's 12 over 13, the decimal for which is 0.923. The tangent would be the opposite side over the adjacent side, that's going to be the 5 over the 12. We have approximately 0.417. From beta, so you have a couple options here. You could either just change colors, which I think is what I'll do, and then I'm going from beta over here. So now this side over here, the 12, is no longer the adjacent, it's the opposite, because I'm looking at the triangle from beta. Hypotenuse does not change, because it's always opposite the right angle, but the opposite side will have to change to being the adjacent side, because I'm now looking at angle beta, not angle theta. So sine of beta, from beta, opposite is 12, hypotenuse is 13, so 12/13. I would just look up above at cosine theta and notice that they're the same, and so it's 0.923. Cosine beta is adjacent, which is 5 over hypotenuse, so 5 over 13, which is going to be our 0.385. And tangent, opposite 12 over adjacent 5, which is going to be, I believe, 2.4. All right, so you have a summary to write. Kind of piece together the things from this lesson, put down your thoughts, and use that to study from when quizzes and tests come about.